Hello, Mr. Boothman here. We're going to be talking about section 5.5, which is graphing sine and cosine functions. I'm going to split this up into two different videos because this is a bit of a lengthy section. So here's the first part. Let's jump right in and look at the graph of y equals the sine of x. So the trig functions are just that. They're functions. My inputs are angle values, and then my outputs are coming from those points on the unit circle, if they're special angles, the ones that we memorize for the unit circle, or our calculator will give us the value if it's not one of our special points. So for 0, pi over 2, pi, 3 pi over 2, 2 pi, and then the negatives in our table here, those are going to come from the terminal points on the unit circle. 1, 0, 0, 1, negative 1, 0, and 0, negative 1. So if I plug in 0, the sine of 0, it's going to be right here. The sine is the y value, so my output is 0. Plug in pi over 2, my output will be 1, and so on. And then if I go the negative direction, it's going to be very similar. So I can plot those points. 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, 2 pi there. And then the negative direction. That's the sine function. It looks like a wave. We call it the sine wave. So some basic properties of this graph. Well, the domain we can see is all real numbers. You can plug in any x value. I can plug in any angle into the sine function and I'll get something back. The range, my highest value is positive 1, and my lowest value is negative 1. The range is possible y values, the outputs that I get. So I'm going from negative 1 to 1. The period, period in trig functions is how long it takes for the wave to repeat. So we can see from here to here, that's one full wave. And then from here to here is another full wave. It repeats. So here the period for the sine wave is 2 pi. We can look at our x-intercepts. So here, here, here. I'm repeating, or I'm crossing the x-axis every pi. So x-intercept, every x equals pi, and we're going to say k pi. K is just an integer. And that's just our special math way of saying that every multiple of pi is when I'm repeating my x-intercept, when I'm crossing the x-axis. My y-intercept, I'm just crossing the y-axis here, y equals 0. We can talk about the symmetry of the graph. If you recall all the way back last semester, we talked about functions being even or odd. If a function was even, then it's symmetric with respect to the y-axis. If a function is odd, it's symmetric with respect to the origin. It turns out that the sine function, we can see, is symmetric with respect to the origin. So symmetry for this, odd. And if you remember, the definition we used was that f of negative x equals negative f of x. F of x in this case is the sine function. And then finally, number 7, what we call the amplitude of the graph is 1. That's how from the middle of the graph, so in this case from the x-axis, the amplitude is how tall the wave is. So in this case, it's 1. We're going to talk more about amplitude later in this video. But those are some basic properties of the sine function. Now we can talk about the cosine function. Again, we're going to get our y values the same way we did before, except this time cosine is going to be the x values. So 1, 0, negative 1, 0, 1. Then going back the other way. So we start at 1, go down, And then here, repeats. It's a lot harder to draw a smooth curve electronically than you would think. So there's my cosine function. And just like the sine function, we can find a bunch of different properties. The domain is, again, all real numbers. The range is still -1 to 1. Those are still my possible y values. The period, the wave repeats, still every 2 pi. My x-intercept, this time, a little more complicated. They're starting at pi over 2, right here, and then it takes another pi to repeat them. Okay, don't worry too much about that. I wouldn't ask you many questions like that, but do talk to me if you're interested. We can talk about the y-intercept. I'm crossing the y-axis here, this time at y equals 1. And then back to symmetry. So this graph, it doesn't look like it from my sketch here, but it is symmetric with respect to the y-axis. That makes this even. And if you remember, our definition for that, what we used to find that was f of negative x equals f of x. And that's true. If I plug in pi over 2, that's the same value as cosine of negative pi over 2. So it's even, symmetric with respect to the y-axis. And then again, my amplitude is 1. My height is 1. So we're going to dig into this a lot more. This first video, we're just going to focus on talking about the two things we just discussed, amplitude and period, and then we'll talk about other kinds of transformations in the second video for this section. So to start, let's talk about the standard form of the sine and cosine function. Now, in class, we built this up by pieces. Right now, I'm just going to give you the whole standard form of sine and cosine, and then we can break it down in a minute. So I'll explain what all of this means once I'm done writing it. So basically, A is the amplitude, B is going to change the period, C is going to move the function horizontally, and then D will move the function vertically. So pretend this has nothing to do with trig functions. We've been talking about transformations for a while now, first all the way back in Unit 1, and then we talked about it again when we talked about polynomials, and then logarithms and exponential functions, and so on. And the rules are the exact same here. Here I'm in the parentheses, so I'm affecting x. These are horizontal transformations. Multiplying x by something, in this case whatever b is going to horizontally stretch or compress the graph. Adding or subtracting a number to x is going to shift the graph horizontally. And then I'm in the parentheses, I end up doing the opposite of what it's telling me to do. So if it's plus a value, I'm actually subtracting that from my x values. Now, a and d are outside the parentheses. They're affecting y. A is a vertical stretch or compression. And then D is a vertical shift up or down. I'm outside the parentheses. I'm just doing what it tells me. If it says +2, then I'm moving the graph up 2. In trig, we have special names for these transformations. So that's most of what the trickiness here is. Starting with amplitude, we define amplitude as the absolute value of A from the standard form. And this is just how tall the graph is, the wave is, from the midline. So the midline is that line that was right in the middle of the graph, right in the middle of the wave. It's usually the x-axis, but it changes if we move the graph up or down. So from that midline up to the highest point on the wave or down to the lowest point on the wave is my amplitude. It's the vertical stretch or compression. So if I have a function y equals 2 times the sine of x, the amplitude is 2. So what that means is instead of going up 1, I'm going up 2 or down 2. I've stretched the graph vertically. So if we go down here, the amplitude of this function is 4. The amplitude of this function is 2. It's just the absolute value of a right there in front of sine or cosine. So amplitude is probably the easiest transformation to look at. And really, just think about it as the height of the function. Period is a little different, just a little. The period has a special symbol. It looks like a W, but it's really a lowercase Greek omega letter. So this is omega. It's what we use to describe or to write period. Equals the normal period for the function. So we saw for sine and cosine, that's 2 pi. Over the absolute value of b in the standard form. So that b, that was up here, from standard form. And the period is how long it takes for the graph to repeat. So if I have a b value instead, so y equals the sine of 2x, then my period is 2 pi over the absolute value of 2, which is 2 pi over 2, which is pi. So the function is repeating every pi instead of every 2 pi. So I'm compressing the entire graph like this. It repeats far more often. And just like our transformations before, I'm in the parentheses, I'm doing what it tells, or I'm doing the opposite of what it's telling me. So sine of 2x, I'm multiplying x by 2. You would think that that means I'm stretching the graph by a factor of 2. But really what's happening is that I am compressing the graph by a factor of the reciprocal, 1/2. Why? Well, we can see how that's changing the period here. So to find the period down here, my b is 1/2, so I have the period equals 2 pi over 1/2. When I divide by anything, I'm multiplying by the reciprocal, so that's 4 pi. Here, b is 2, so my period ends up being pi. And then here's for you to try on your own. At least just tell me the amplitude and period. And now down here, let's go ahead and try to graph a couple of these. There's a lot of them. The ones that I would like you to do in order to do our retake are 2, 3, and 8. I'm going to go through numbers 1 and 5 right now, and then 4, 6, and 7 are just additional practice for you. And then that'll be it for this part of the section for this particular video. So let's look at number 1. I know Ms. Parker teaches this in a different way than I do. I like being able to directly see how I'm changing x and y. We kind of did this with logs and exponentials last semester, Unit 3. But for trig functions, I just think it helps us see exactly what's going on. So I'm going to take my normal points, and I'm not going to do the negatives. I'm only going to do this for one period. My normal points, my normal table for just the sine function, y equals the sine of x. So that's what those points would look like. And then I'm going to transform these points following my transformations. So I have this 2 here in front that's affecting y, and I'm doing what it tells me. It's a vertical stretch by a factor of 2. So I'm taking all of my y values and I'm multiplying them by 2. And so now I have my transformed points. So if I plot these points, and I do apologize, this should be pi over 2, pi, 3 pi over 2, and 2 pi. My new points have taken into account all my transformations already. So I don't have to, if you're really comfortable with just knowing the sine function and then you see, oh, there's the a is 2, that means the amplitude is 2, so I'm just stretching it vertically, like that's fine. But I do think as we add more and more transformations, it gets a little more complicated. It's a good idea to show your points and keep track of everything going on. So let's do number 5 now. Number 5 is, I don't have an a. A is 1, so my period is still 2 pi. But I do have a b value. In this case, b is 2. So again, start with our normal table of values. And then my b value is changing the period. So let's look at how that changes the period. Period is 2 pi over the absolute value of 2, which is pi. So when I go to change my x values, when I change the period, I'm going to completely ignore my existing x values. I was going from 0 to 2 pi, but this time that's completely different. I'm actually going from 0 to pi. And before going from 0 to 2 pi, I needed 4 equal steps to get there. Right? 0, pi over 2, pi, 3 pi over 2, 2 pi. I was adding pi over 2 each time. I still need 4 equal steps, but this time I'm going from 0 to pi. So in this case, it's pretty simple to see, but if you get a weird period, here's my rule, here's my advice for you. Take your new period and divide it by 4, and that will give you what you're adding each time. To get your new x values. So start at 0, add pi over 4. So I get pi over 4. And then add another pi over 4, 2 pi over 4, or pi over 2. Add pi over 4 and I get 3 pi over 4. Add pi over 4 and I get 4 pi over 4, or pi. I'm not changing y in this case, so now I have my new points. 0, 0, pi over 4, 1, pi over 2, 0, 3 pi over 4, negative 1, and then pi, 0. I've compressed the graph. I've cut the period in half. All right. That was kind of a lot. Go ahead and rewatch parts that confused you. I know we've already covered this in class, so most of you should be comfortable with this. This is just kind of if you're still struggling with anything. And let me know if you have questions. I'm here. Otherwise, I'll be back for the second part of this in a minute. Thanks so much.